Hello my dear friends, today we will see the new concept steps to solve numericals on beams. Here, before starting these steps, we need to understand the thing what you mean beam. What do you mean by beam? Beam is a horizontal member which is used to carry the vertical loads and as well as torsional loads. And usually beams are meant to carry only the transverse load and the rotational loads, whereas bars are used to carry the axial loads. The main difference between beams and bars is beams are meant to carry the vertical loads and these bars are used to carry the axial loads. Here we'll see the steps to solve the numericals on beams. The first step is to modeling and discretization. Let us consider a simple bar beam element, cantilever beam. Here if you see, it has a span length of 1 meter and 2 meter and it is subjected to UDL. Clear? So here we model this entire cantilever beam into two elements, because here if you see, the application of load is at only the 2 meter span and 1 meter is free, and wherever there is a load there we insert a node, in the sense we create a node. So there if you create a node over here, it becomes two elements. So again, as we see in the earlier that bar element has, each node has one displacement, means 1 degree of freedom. Here in the beam we have each node has 2 degree of freedom, means as I said earlier, beams are meant to carry vertical loads as well as torsional loads. Each node has two types of displacement. One is vertical displacement and one is the torsional displacement. Vertical displacement, torsional displacement, vertical displacement, torsional displacement. This is how each node of the beam acts like. Again, this type of beam like beams, usually these are subjected to the vertical force F and twisting moment M. Vertical force F as well as twisting moment M in each node. So that's what we have written here. This is nothing but our modeling. If you see here, we have displacement V1 because of force F1, we have displacement V2 because of force F2, we have displacement V3 because of force F3 at each node, that is node 1, 2 and 3 respectively. Here we have angular displacement theta 1 because of moment M1 at node 1. Here angular displacement theta 2 because of load, that bending moment M2, and we have angular displacement theta 3 because of moment M3. Clear? This is how we need to do the modeling. If suppose we have a cantilever beam and it has only the point load, then at point load at the extreme end, what we do, we consider the whole beam as single element. Since here we have one another load, that is UDL, which is acting for certain length, that is 2 meter, we need to create a node over there. So we have created, this is first element, this is second element. Clear? Why we have created two elements over here. Once we do that, next step is to determine the element stiffness matrix. The element stiffness matrix for the beam element is given by E into I divided by L cube. L cube is nothing but length of the element, E is the Young's modulus, I is the moment of inertia, and these are the elements in the matrix 12, 6 le 6 le in the sense le is nothing but length of the element minus 12 6 le. This equation, this matrix we found by deriving the equation, by deriving the stiffness matrix derivation for this beam element. So this is the derivation, from there we got this stiffness matrix. So these are the elements which we need to remember to solve the beam problem. E, I, Le cube, and these elements we need to remember. Again, as I said earlier, this is a symmetric matrix. You need to remember only the upper diagonal elements. If you remember the upper diagonal elements, the same we have the lower diagonal elements. Same we have lower diagonal elements. Once you determine the stiffness matrix for each element, the next step is to formulate the global stiffness matrix, where what we do, we add these stiffness matrix for each element. Once we do, we will get the global stiffness matrix. After that, we need to define the global displacement vector. Here for this type of beam, for example, this is our cantilever beam subjected to UDL over here, and we consider this as first element, this as second element. Then what we do here, we have displacement V1 and theta 1. Here we have displacement at node 2, we have displacement V2 theta 2. Here we have displacement V3 and theta 3. Like that we need to define, like for example, this is first element, this is second element. We have V1 because of force F1, theta 1 because of moment M1. Similarly for second node and third node. That's what we have written. This is the vertical displacement, this is the angular displacement at node 1. Vertical displacement, angular displacement at node 2. Vertical displacement, angular displacement at node 3. We have written transpose because it is a vertical matrix. We have written in the horizontal manner, so we have taken it as transpose. Now we have now we need to determine global load vector. If the beam, for example, if this cantilever beam subjected to point load, we use this formula. If it is subjected to point load like this, if we consider two elements, then we use this formula F1 M1, F2 M2, F3 M3. If we have two elements, if we have only one element, for example, this is a cantilever beam, we have the point load at the extreme end. If we consider only one element, then what we do, we need to define the global load vector. F is equal to, how we will define, actually it is F1 M1 F2 M2. So this is how we need to define the global load vector. Now for for the example what we have taken, there we have three nodes. We have 1 2 3 nodes, so we have F1 M1 F2 M2 F3 M3. so it is transpose over here. Like in the given problem, the second second element, that is UDL. In the given taken assumption, like we have taken some example over there, the second element is subject to UDL. To calculate the forces due to application of UDL, we have this formula. Like this is nothing but PL by 2 PL square by 12 PL by 2 minus PL square by 2, where P is the intensity of load, L is the length of the element, and this is the formula. This is the formula to calculate the force when it is subjected to UDL, right? You just keep on noting these formulas. Next step is to write on the equilibrium equation. As you know that stiffness is equal to load divided by displacement. So what we have done, stiffness into displacement, which is equal to load. That's what the equilibrium equation, where K is the global stiffness matrix, U is the global displacement vector, F is the global force vector. Once we do this, once we write equilibrium equation, The next step is to apply the boundary condition, where like we usually approach the elimination approach. We usually try to handle the boundary condition by this method, elimination approach. What we do, wherever the nodes are fixed, for example, for the given problem, here we have a roller support, here we have a roller support, and it is fixed over here. So here here v1 is fixed, theta 1 is fixed. Here we have horizontal displacement, means we have deflection in theta 2 direction. Here we have deflection in theta 3 direction, whereas v2 is fixed, v3 is fixed. So we need to eliminate corresponding rows and columns of the nodes wherever these are fixed. Once we apply the boundary condition, then we'll get the equation. If you solve those equation, we'll get the slope is nothing but the deflection theta 1, theta 2. These are the slopes or angular displacement we'll get in terms of radians. Once we calculate that, the next step is to determine the reactions. As already seen, the formula K into U minus F. This is the formula where we can calculate the reaction at the beam. So these are the steps to solve the beam problems. If you have any doubt in this, let me know, comment below, so that I can answer your question. Watch my further video, which is nothing but I am going to solve a problem from the video question paper on beam. Thank you for watching.